Okay, welcome to another lecture video of OpenStax Astronomy. We're going to be looking at Chapter 22, Stars from Adolescence to Old Age. And so we'll begin with evolution from the main sequence to red giants. So to see what happens to stars at the end of their life here. So we discussed the HR diagram, and we talked about how on the diagonal is the main sequence. Well, when a star goes towards the end of its life with that helium flash, it becomes a bit unstable. And so these stars will swell up and will move from the main sequence up to this giant and supergiant area. Now, the star isn't actually moving, its location here. What we're doing is we're just plotting it on this graph. So it's moving its location on this actual graph here. So the relationship between all of these characteristics. So we talked about the proton-proton chain, where we have hydrogen turn into helium. Then eventually all of that hydrogen will run out in the core and it will become helium. And we'll have hydrogen now in a shell around it, so kind of in an extra layer. And so when that helium fuses, it kind of does all in one shot, and it turns into what we call a helium flash. It ignites rapidly together. And so it makes everything around it a lot hotter. So now the hydrogen in the shell around it becomes hot enough for that to fuse. So you have this multi-layer that's burning, the helium and then the hydrogen now in a layer outside of it. And so if we look at the HR diagram and we know a star's mass here, we'll be able to predict how large they will actually get, so how much they will end up swelling up. And we've done this now by observations and also calculations. So for example, something with one solar mass, we could kind of follow its path to about how large it will swell up. Our sun, when it swells up, it's going to get fairly large. It will engulf the first three terrestrial planets, so the Earth, and it'll probably get close to about the orbit of Mars. So hate to be a bearer of bad news, but ultimately our sun is going to consume our planet. It's just going to roast it. It's going to get larger and larger, and it will ultimately consume it. Okay. So let's see how that actually looks with we're looking at clusters. So rather than looking at individual stars now, let's consider looking at groups of stars, what we call clusters. And there's two main types of clusters. Globular clusters, which have millions of stars, very dense, compact, and you can see the coloration on them is going to be more of a reddish, yellowish color there. And then we have open clusters, which have a few thousand loosely packed stars, and these are going to be more bluish white in color there. And so what we'll see is that in reality, when clusters form, when stars form, you have both. You have these blue and very bright stars and red fainter stars. Well, ultimately, the blue stars outshine all those fainter objects, and so you're not able to see them. Eventually, the blue stars will die out, they will fade, and then those dimmer stars will come to light. And so all clusters really start off with both, but newer clusters are going to outshine, right, with the blue light. So if we look at these clusters here, these open clusters, the image on the right is going to be newer stars. So it's a newer cluster, as opposed to the globular cluster. These are going to be older stars. And so here we see an image, and we could see that there are some fairly bright bluish white stars here. But now in the background, you could also see some more dimmer reddish stars that are coming to light. So if we look at this cluster and we plot the graphs in the HR diagram, we see that all of the stars in this beginning portion here of the main sequence no longer are there. Those are short-lived, so they already have died out. And so what we see is now these fainter stars are coming to light. And this is helpful because right at this point here, what we call this kind of main sequence turnoff here, is now we could get a date of how old this actual cluster is of stars here by seeing where exactly this new or this new kind of herd of stars are, or this kind of peak here is relative to the lifespan. So when we look at the HR diagram for entire clusters, if we see stars on the entire main sequence, we know it's a newly formed, those are newly formed stars. And then we could date it. Well, if the main sequence turnoff point is at about 100 million years, right about here, right, we could see the age of it, of those stars that actually lived there. If we see the main sequence is about at 10 billion years, so right about here or so, right, there'll be none of these stars in that first portion of the main sequence. So it gives us a date of how old those stars are. And so in this newly formed stars here, we're going to see a lot of blue white stars that are going to outshine everything. Once we have an old cluster here, these stars are going to be more reddish yellow in color. There'll no longer be any blue stars left in that cluster, and so we'll be able to see those fainter objects. And because there are more of these fainter objects, this is why those clusters tend to have more stars inside of them. So let's look at the evolution of low-mass stars. We talked about it swelling up and a helium flash. Well, that's not the entire story. So we will see that a star turns off from the main sequence, that hydrogen will turn into helium, and it will have kind of a helium flash where it swells up. But it burns through that fuel very rapidly, and gravity once again will win and reduce that star. Well, then the fuel now in those shells will light up. They'll get hot enough for those to burn, and the star will swell up one more time. So it's kind of this balance of getting large and small and large again. And then ultimately, it will turn into a planetary nebula where it lets go of all of its remaining gases. So we call this the broken thermostat, where we have that hydrogen turning into helium, right, in the core, but then you get this outer shell. And so that broken thermostat makes the star expand, then contract and expand, and it becomes very, very unstable. And so we see that we will end up with multi-layers, so that hydrogen going into helium, and then we also see that elements could form all the way up into carbon with low mass stars. So you'll have these other elements that keep going into shells, kind of like layers in an onion. And as the first layer sparks, the next layer will become hotter. Well, it could actually fuse its elements, and so on. That would create a chain reaction there. So you have that eventually hydrogen is in the core, then all that turns into helium, and then eventually that helium would turn into carbon. Well, but on the outer layers, it's the same process. You'll have that hydrogen turn into helium as well. And so we not only get burning in the core, but also within the layers there. And that's what creates that unstable or that broken thermostat. And so here's kind of an image where in what stage it actually has that thermostat that breaks. So something like our sun will get larger here, right? A subgiant, a red giant will become smaller and then get large again into that red giant. And then eventually at that point, since carbon is the end of the line with low mass stars, it will start dispersing all of its elements in what we call a planetary nebula. And so planetary nebula, because when it was first observed, it looked round like a planet, but it's really a large amount of gas that's getting dispersed outwards. And this is a fairly long process, takes about 10,000 years or so for that to happen. Then what would happen is a corpse will be left over, a white dwarf, and this will begin to cool down. And so that's why it will move its way over here towards the cooler star. So a slow mass star at the end of its life will again have that helium flash, get unstable. It will turn into a planetary nebula, and then what would be left over will be a white dwarf, which is a corpse of a star. Here are a couple images of planetary nebulas, and we could see that these gases are just getting dispersed. And again, in the center would just be a white dwarf that is left behind, just a core of it. And so this is ejecting all that hydrogen and helium back into space. Stars are very efficient. They only take the fuel they need, and at the end of their life, to give everything back to the universe, and those gases will then form more generations of stars. Here's a summary of low-mass stars. So when they form, they're in the main sequence. Then towards the end, they'll turn into that red giant with that helium core fusion. They'll have that double shell fusion. And then eventually they'll turn into a planetary nebula and leave behind a white dwarf. And so this limit here for low-mass stars, if you recall, brown dwarfs, which are failed stars, are about 0.08 solar masses. So we need at least that much to become a star. And then the limit for these white dwarfs is roughly at about 1.4 solar masses. So that's what we consider low mass stars. So from about 0.08 to about 1.4 solar masses. But there are many stars that have more mass than even our sun or other stars. And so let's look at the evolution of these high mass stars. So things above 1.4 solar masses. And they end their life a little bit more violently. So apart from the proton-proton chain, where hydrogen becomes into helium, in low mass stars, then that helium will turn into carbon. And so that's the end of the line for low mass stars. It only gets so hot that we could create carbon. And so that puts us at about the sixth element. So up to about the sixth element is created in low mass stars because of the heat temperature. High mass stars, so those above 1.4 solar masses, actually have another cycle beyond that, the CNO cycle. And so this creates a higher step in the elements here. And so here's kind of a breakdown of how these end up fusing together. But ultimately, the CNO cycle is talking about the carbon, nitrogen, and oxygen. So those are the next layers that actually get formed. So in those high mass stars, we get higher temperatures, and we're able to form up to about oxygen. Then there's a process called a helium capture. So those elements could now capture a helium as well. As you recall, hydrogen formed into helium, right, with 4 protons. So we could capture one of those, and they could create heavier elements, all the way up to neon and then magnesium as well. So up to about the 12th element there. So that helium capture could build beyond that CNO cycle. And then for stars that are even more massive, we're talking about over 8 solar masses here, we could have advanced nuclear burning. And so this will actually capture some of those carbons and oxygens will merge together, and we could create elements all the way up to iron. So silicon, sulfur, calcium, up to iron, which is a 26th element. So in low mass stars, carbon is the end of the line. In these high mass stars, and specifically those over 8 solar masses, you could get up until iron, the 26th element there. And that's the end of the line for elements or reactions within the star inside of there. So similarly, you have this multi-shell burning, but with more elements. And so this causes those flashes, right, for those layers to start igniting. And what happens, it becomes very unstable. You have a lot of fuel, and a lot of it starts to just ignite at these very high temperatures. And so when finally that iron is created, a star really only has minutes to live at that point. And so what happens is a high mass star will end its life in a violent explosion, what we call a supernova explosion. And what will be left behind is just a bunch of neutrinos, what we call a neutron star, would be the corpse of a high mass star. And so in this supernova explosion, you have all of these elements that are thrown out, and you get these huge clouds of gas that are being dispersed in all directions. And so here's an image, again, some of that coloration added with the different wavelengths, so we could see all of the gases that are being dispersed. These are not only extremely bright, but lasts a long time. The Crab Nebula here is kind of the remains of a supernova from about 1000 AD. So we could still see that there. So the supernovas exploding these high mass stars. And so it's at these extreme temperatures that you could form elements beyond iron. So all of the other elements beyond iron formed inside of a supernova, an exploding star. So if you have a gold ring or a gold chain, that gold could only be produced inside an exploding star, so inside of a supernova. So that's saying that we come from stardust is actually correct. These later generations of stars now have heavier elements, and that's what's able to form things like the terrestrial planets. So our sun is definitely a later generation star. Earlier generation stars, first generation stars, were just primarily hydrogen and helium. So the life summary for high mass stars is off the main sequence there. They also become the red supergiants Again, they become unstable with that helium flash as well, but they have that multi-shell burning of more stages, right? Those more elements. And at the end of their life, they blow up as a supernova, and what they leave behind as a corpse is a neutron star.